Today we're going to dive into the relationship between polynomials, linear factors, and zeros. And the first thing I have up here is an equivalency theorem. So it says the following statements about b and a polynomial are all equivalent. And this is the polynomial. Here's that standard form of a polynomial that we've talked about in other videos. So the four statements that they have here, and I highlighted the keywords here. X minus b is referred to as a linear factor of p of x. B is also referred to as a zero of a polynomial. B is also referred to as a root or a solution of that polynomial. And b is also referred to as an x-intercept. All four of these statements, even though they require just a little bit different methods, are all referring to the same thing. So if somebody asks for an x-intercept, that's the same as looking for a zero. Or if they say, find a factor, that's the same as finding a solution. For the most part, they're equivalent type of statements. The other thing that shows up here is this factor theorem. It says the expression x minus a is a factor of the polynomial if and only if the value of a is a zero of the related polynomial. So it kind of goes along with this idea of factor and zero being very similar things, or sometimes seen as equivalent. So let's take a look at some examples with their instructions. So the first set of problems I have here says factor. So I have to go back to my factoring skills. It looks like they have an x in common, so I'm going to take that out first. And what's left in there is still factorable. I can still do another set of factoring here. And now it's factored. Okay? Those answers that are there, we could also use them to find zeros, roots, solutions, x-intercepts, but this time we're factoring. Number 2 up there starts out the same way. I can take out an x. And what's left does factor a little farther, and I get 3 pieces here. But it makes sense because both of those were cubics, which means a power of 3, and they had 3 linear factors. Now my second set here says find the zeros. Now you'll notice they're already factored, so they're kind of in the same form that these are, but now they want me to find zeros, and you're thinking, well, you said factors and zeros are the same thing. They're equivalent. They're not the same. So I need to take this one more step and set each factor equal to 0. So I can actually find solutions or answers or roots. Looks like -2 is a 0. 1 is a 0. And 3 is a 0. So this had 3 zeros, 3 answers, 3 solutions, because it had the 3 factors. Now, the more we do this, the more efficient we get at it. This is going to be -5. This is going to be 3. But sometimes this one in front throws people off. They're like, well, it's just an x. There's nothing to solve there. Well, I got to these answers by setting them equal to 0 and solving. So let's set this equal to 0. It's already solved. So this has 3 zeros, -5, +3, and 0. Now, if I take this equivalence theorem and I think about where the x-intercepts are at, they're going to be at 0, 3, and -5. So if I'm a visual person and I like to look at the graph this, and you're going to see that's where it crosses the x-axis. Those are the zeros. Those are the roots. Those are the solutions. Those are the factors. We're talking the same language. Now let's find an application for this. This factor theorem, where it says, if I have a factor, that means it's a 0. But what if I give you the zeros, the answers? And I want to know where they came from. So I kind of turned it around on you. You already have the answers. So let's think of this process working backwards. If I move this 2 over, I get x plus 2 equals 0. And if I move this 2 over, I get x minus 2 equals 0. And if I move this 3 over, I get x minus 3 equals 0. So they're all equal to 0 now, just like they were up here. And if I'm working backwards, I'm going to take the zeros out, and I'm going to multiply these factors together. So I'm going to take x plus 2 times x minus 2 times x minus 3, and I now have this polynomial. And if I would actually multiply this out, use your FOIL, use your box method skills, multiply this out. This one's an easy one because it's that difference of squares pattern. But keep going. FOIL this one out, or box method this last one out, and you're going to get an x cubed. You're going to get a 3x squared. You're going to get a 4x, and you're going to get a 12. That cubic polynomial is where these 3 answers came from. So they might give me something and ask me to factor it, or maybe go a little farther and actually find the zeros, but they could give me the zeros and tell me to go back to where that polynomial came from. Now, there are some things that make this easier. Okay? If I take a look at this one right here, I'm going to start with these last 2. Because that's the difference of squares. Then I'm going to multiply this other one in. That cubic polynomial, x cubed minus 3x squared minus 9x plus 27, that's the polynomial that produces those 3 zeros. Now that last problem that we did had 2 x equals 3 answers. That has a special name when we talk about polynomials. They're known as multiplicities, or multiple zeros. Here's the definition. If a is a zero of multiplicity n in this polynomial, then the behavior of the graph at the x-intercept will be linear when n is 1, quadratic when n is 2, cubic when n is 3, etc., etc. Okay? We'll get to that. That's a little more advanced. What we want to tackle first is this concept of multiplicities. Now, if I need to factor first, I'm going to factor. These all have an x squared in common, so I'm going to take that out. And what's left still factors. So I have my x squared, I have an x minus 4, and an x plus 2. So now it's in factored form. And you'll notice that this one has a power of 1. So that means x equals negative 2 only shows up once. This one has a power of 1. So x equals 4 only shows up once. But our multiplicity, our multiple root, shows up right here. When I set this equal to 0 and solve, I get 0, but I get it 2 times because of the squared. So it has a multiple 0, a multiple root at x equals 0. Now, when you have to do your own factoring, sometimes it's not as easy to see. So let's look at one that's already factored. This one's already factored. This is going to have an answer of 0. It's going to have an answer of negative 4. And it's going to have an answer of 2. Okay, that's not hard to solve. But now when we look at these powers, that 2 is going to show up 5 times. Remember, powers are just shorthand for repeated multiplication. So this is x minus 2, x minus 2, x minus 2. There's 5 of them. That's our multiple root. 2 shows up 5 times. Here, negative 4 is going to show up 2 times. And x equals 0 is just a single root because there is no power. The little different than this one because the first one, 0, had a squared. That's why it showed up twice. These are called multiplicities. Now, the crazy part about this, and this is for visual learners especially, if you would graph this polynomial, when it has double roots, when it has multiple roots, if it only has a single root, like this is only once, it's going to look linear when it crosses the x-axis. It's going to look like a line. So when it crosses at 0, it's going to look like a line going through 0. But when it has a double root, a second multiplicity, when it hits that line, it looks like a quadratic. Even though it's touching once, it actually has a double root. If it looks like a cubic when it hits the line, even though it only touches once, it has 3 roots there. It's because it looks like a cubic. So this is kind of an advanced, a really 4.0 thinking. It's for when you're looking at graphs. We're going to focus in on those exponents and go -4 twice, +2 5 times, no powers here. It's just once. It's just a single root like we would expect. Now the other thing we need to talk about is this idea of maximums and minimums. Now when we first introduced polynomials, we talked about the peaks and the valleys, and we said we weren't interested in those as much. We looked at end behavior. But now we're going to take a look at what happens between the ends when it changes direction. So a relative maximum is defined as the value where it goes from up to down turning. Okay? I think of these as the hills or the mountain peaks. Okay? If you see something that looks like a hill, at some point it goes from going up to going down. That's a relative maximum. Now a relative minimum, same thing but the other way. It's going down and changes to up. I call those valleys. So if I have something like this cubic here, there's a peak here, a maximum. There's a valley here, that's a minimum. And they're relative. They're not absolute maximums or absolute minimums. They're just relative. But it goes from up to down, and over here it goes down to up. That's how they're defined. We're going to do this visually. Okay, we're going to graph this. So we're going to put this polynomial into our grapher, whether it's a calculator, whether it's Desmos, something that we can graph, and we're going to look for when it peaks and when it valleys. Now you'll notice that the peak happens at this point right here. That is the maximum, the relative maximum, where it gets to its highest point. Excuse me, I think that's the minimum. That's where it bottoms out. -4, -80. It bottoms out. The minimum occurs at 228. Now there's my maximum. And if you graph and look for these 2 points, you'll see where one's a peak, one's the highest point, one's a valley, it's the bottom point. That's what we're looking for when we talk about maximums and minimums. When we talked about quadratics, we looked at it from the vertex point of view. That was a maximum or a minimum. Now we have multiple ones because we have cubics, we have fourth powers, we have much bigger powers to deal with. If you take some time, pause the video and graph this one, you're going to see the same thing. But they're not as nice of points. They aren't always the cleanest points. They aren't always integers. But this one has 2 points where it peaks and where it valleys. One of them is at -0.86, 3.13. The other one is at 0.64 and -2. Here's a maximum, here's a minimum. Now be careful of what they ask for. If they ask where the maximum and minimum occurs, they're looking for the point and especially the x value. If they're asking for what the maximum or what the minimum value is, they're looking for the y. This is the highest y value. This is the lowest y value. It depends on what they're asking for. But maximums and minimums, the relative kind, are peaks and valleys.